Students, good morning. So for today's experiment, thank you, Sukhrit. So for today's experiment, we will be looking into experiment number 6, okay, which is nothing but your realization of 1 or 2-bit comparator and how your IC 7485 works in helping this comparison done. Now, I think all of you would have studied your magnitude comparator in your theory classes, haven't you all? Yes, I want you all to be interactive. Have you all studied your magnitude comparator in your theory classes?
I don't think so, sir.
Magnitude comparator, A is less than B, A is equal to B, A is greater than B. Now, do you remember? Yes? Okay, fine. So, um, so this magnitude comparator, okay, is actually helpful in checking two values, okay, between A and B, and it will tell if in case A's value is greater than B, or if both A and B values are equal, or if B is greater than A or A is less than B. Okay, so this will be done with the help of magnitude comparator, right? So ultimately, what is magnitude? Can someone tell me what's the magnitude?
That's the value, sir.
Yes, it's the value as to how much it holds. Okay, for example, if I tell you to compare between 3 and 6, okay, A is equal to 3 and B is equal to 6, then you will ultimately see that B is greater than A or A is less than B, right? Okay. So for today's experiment, we'll be using the trainer kit, okay, and the IC7485, which is also called a magnitude comparator. Then we'll be using 7408 AND gate, then 32, which is OR gate, and 04 inverter, 86 XOR gate, and 00, which is AND gate, all 74 series, right? A magnitude comparator is a combination circuit that comprises two numbers. Okay, so let us consider A and B as two numbers. Okay, so it tries and compares the values between both of them and determines their relative magnitude. So it will, this is going to be our result. Okay, so ultimately it is checking if these values are, you know, validated. If one of these values are true. So let's say if A is equal to 2 and if B is equal to 3, okay, which one should go high? The first, second, or the third one?
B is greater than A. Third one.
Third one should go high, right? Okay. So accordingly, if in case now I change the value to 3, okay, then the second one would go high. Suppose I change the value here to say 5, okay, then I would say that the first one holds good, right? So it will try and compare the values. Of course, we are putting here in our decimal form, but here it's all going to be in binary ones and zeros. Okay, it's all going to be in ones and zeros, right? Right. So now what we will do is we will take 2-bit combination, okay, 00011011. And for this combination, we will have 3 columns. Okay, one we will be using for A is greater than B. Okay, and the other one will be using A is less than B, and the last one will be using for A is equal to B. Okay, so now you should compare the values, okay, in the input side now. So which means you should have a logical separation. Okay, you should try to compare only these values. Only these values you should compare. Only these values. Okay. So now let us start with the first one. Now in the first one, now A and B both have 0, right? So what does it mean? Is A greater or B greater? The first case.
A equal to B.
Yes, because both are equal, so it has 0, 0. So A equal to B goes high. Okay. Similarly, now in the second case, A is equal to 0 and B is equal to 1. So obviously, we know that your A is less than B. Okay. Now for the other case, okay, it's going to be reverse, which means A is higher than B. So A is greater than B. Now for the last case also, it is the same as 0, 0. Okay. So which means A is equal to B. Any confusion, students, as to how we got this truth table?
No, sir.
Yeah, is it clear? Fine. So now what we will do is we have the values here. Okay. So once we have these values, we will be using it for developing our K-map. Okay. So these values will be used separately. A is less than B, greater than B, and then equal to B. So these values will be put in K-map. Now here directly for this one, directly you can say for A is greater than B, okay, I can get this equation. Yes or no? Because A is high, okay, B is low. So which means it will be A, B bar. Any confusion? Any confusion?
No, sir.
Yes. So this equation is validated. Now for less than B also, okay, you can just check one value is here. Okay, so when is this going high? When A is less and when B is high. So which means A bar B. Okay, so that value will come here, which is A bar B. Similarly, now I have two ones. Okay, I have two ones for A is equal to B. I have one thing here and the other thing here. So what I have to do, I have to add them up. So for A bar and B bar, okay, the value is going high. So this one I will put it up here as A bar and B bar plus, okay, plus when A and B both are high. Okay, how am I checking? Across the row where I'm getting high and across this column. So ultimately, when AB is high, I will take it as AB. Any confusion, students? Is it clear?
Yes, sir.
Okay, fine then. So we will proceed now and we will see as to how this can be implemented. Now directly when you look at this equation, okay, you can understand that you need an AND gate, something which multiplies, and you need a gate which inverts, right? You need a gate which adds. So you need an OR gate, you need an inverter, and you need a AND gate, right? So all these are implemented with our circuit here. Okay, now you just compare with A is greater than B, A B bar, okay, greater than B. So A is taken from here, A, okay, so A is here, okay, and I want B bar. So B is here, B bar is here. So ultimately I'm getting A into what? B bar, right? So which means this is validated. It's validating for equation A is greater than B. Okay, so We will continue our discussion with regards to the expressions. Okay. So similarly now you can see that for A is less than B, okay, you have A bar B. So which means you will need an inverter and you will need an AND gate together, right? So you have A bar B, right? So this for A less than B, okay. So here you have A bar which is coming in, okay. Here you have A bar which is coming in, and then you have B connected here, okay. So ultimately you will have your A bar into B, okay. So this suffices for A is less than B, okay. So similarly now if you look for the equation, okay, which is for A is equal to B, okay, I have two expressions here, okay, A bar B bar plus AB. So it's nothing but your XNOR operation, okay, and ultimately we need inverters, okay, inverting A value and B value, and also we need the non-inverted form or the original true form of A and B, okay. So we will be using an OR gate here, okay. So we'll be using an OR gate, and the outputs that were there previously, since I've already got your A bar B here, okay, and again that is going to get multiplied with the equation of your A is greater than B, okay, greater than B, okay. So I'm going to add both of them, okay, and I'm going to use an inverter. So XOR becomes XNOR, and ultimately, okay, I'll be getting the expression A is equal to B. So students, any doubts here? Any doubts as to how we
Sir.
got A is equal to B?
No, sir.
Okay, fine. So ultimately what we should do here is we should try and understand the expression, okay, and we can make use of these expressions which are already available. See, for example, here in this expression, what we can also do is we can take the true form of AB, okay, and we can take the complemented form of them. That is one way of doing it, okay. The other way of doing it is just add these two, okay, just add these two, and using your De Morgan's theorem, okay, you can actually obtain this expression, okay. So what is De Morgan's theorem? Can someone tell me? Maheshwar, can you tell me what is De Morgan's theorem? You have studied this, right, in your initial classes, your introductory classes of digital electronic circuits. What's De Morgan's theorem? Maheshwar, anybody else wants to respond?
Sir, complement of A dot B is A
Hmm.
bar plus B bar.
Good, good. Thank you, Supreet. So we are using this property here, okay, and we are trying to employ this property, and ultimately through the inverter, okay, we are able to change this equation, okay, right. Now this was for your just one bit comparison, okay. So wherein I have just A is equal to 0 and B is equal to 0. Now if I increase the number of bits, okay, of course your expressions also are going to change. Not only that, even your circuitry is also going to get much more complex. One more thing that you can see here is, okay, the numbers are given, okay. These numbers are nothing but your pin numbers, okay, corresponding pin numbers. And when you're using your breadboard or your IC trainer kit, okay, when you're employing these ICs, you will have to use these pin numbers, and accordingly you will have to connect them, okay. So Here, for example, okay, in my OR gate, I'll be taking pin 1 and 2, and output is obtained from pin number 3. Similarly, from my inverter 7404, I'll be connecting this pin of 3 of my OR gate with pin 5, okay, of NOT gate. So ultimately, we have to make sure that the pin numbers are proper. Okay, so for that we will have to remember as to where is going to be my input and where is going to be my output. Okay, so all this should be kept in mind, and accordingly you can uh, get proper output. Sometimes I've seen students, okay, connecting to the wrong terminals of inputs and trying to obtain output from a different terminal, which doesn't work out, right? So just make sure that you are aware of all these numbering, right? So now let us increase the number of bits, okay? And we'll try and understand as to how this can be done. Similarly here, instead of 1 bit, okay, I will have 2 bits, okay, which is A1, A0, and B1, B0. So so here also, okay, what you can do is you can think of a logical separator, okay, here, and A naught and A1, okay, can be treated alone as A, okay, and B1 B naught can be treated alone as B, okay. So together it's taken as A, and together these two are taken as B, okay. Fine. So if we can draw a line here, okay, so that will be easy for you in understanding or separating the values between A and B. Okay. So the same concept applies here, okay, wherein we'll be looking at values at individual rows. Okay. So at this row you have 0 0 for A, okay, and for b0 and b1 also you have 0 0, so which means it suffices to value a is equal to b, right? Similarly, now in the second case, if you can see, okay, can someone tell me what is the value of a here in the second case? What's the value of a?
A bar, sir.
No, a is how much? I'm just asking the value here. How much is a? Is
0,
it
sir.
0 or is it 1 or
Zero,
is it 2?
zero, zero, sir.
It's only 0, right? And what about b?
1.
Yes, so which means b is
1.
having a higher value, okay, so it tells us that a is less than b. So this is how you are comparing, okay, between the values of a and b, okay. So I hope this truth table is understood, right? Yes, you want me to explain all the cases here?
No, sir.
Okay, fine. So let's take another case here, okay. um, yeah, another case here. So in this case, I have 1 0 and I have 0 1. So among these two, now you have one of them to be 0, you have one of them to be 1. Here also you have 1 0 and then you have 1 1. Now how do you compare these values? How do you say that which one is higher and which one is lower? Chandan, how do you come out and decide as to how these values are taken? Which one is high and how it is low? Can you compare for this value? Yes, Chandan,
Sir,
go ahead.
Yes,
A
sir.
is 2, sir.
Okay,
B is 1, sir.
good, good. So in this way, we will have to think of, okay. So that is why I've drawn this red line wherein you can differentiate between these two values, okay. And ultimately, since the value of A is higher, because this is having a higher order, right? See, because it starts from LSB, okay, and then it moves to a higher order MSB, right? So I am having a high value at MSB, right? So which means this is having more value. Okay, MSB is having more value. So I will be taking A as greater than B. Fine, right? So similarly, you can take this case also. Okay, here also you can see that it has 2 1s. Okay, so obviously your A will be less than B. Okay, right. Now, having all these truth table worked out. Okay, so you can again make use of your different techniques. Okay, either you can make use of k-map, or you can even make use of your implementation table, or in any method for that matter. Okay, and you can entry these values into k-map, so which means each separate mm, constraints, okay, will be actually using a key map. For example, your uh, greater than b, okay, will be having one key map. Your less than b will be having another key map, and your equal to b will have another key map. Okay, so equal to b, we are using this key map. Okay, just you have to make sure that where there are ones, okay, only there you'll be filling. Okay, so here we have at 0. Okay, similarly here, okay, we have at this value 5. Okay, so 0 1 2 3 4 5. So at the fifth value I will actually bring it up. Okay, so ultimately these values, whatever values are here, okay, will be filled up into your key map. Okay, so you can look for grouping here, since diagonally we don't group in your Karnaugh map. Okay, so it's not possible for us. So ultimately we come up with a equation which is giving us for a is equal to b. And similarly for a is greater than b, okay, we use another key map, okay, which is here. Okay, a little bit of grouping is possible here. Okay, wherein I can get a quad, okay, 4 ones, and then I can get 2 ones here. Okay, and also I can get 2 ones here. Okay, so with this I will be again getting my equations corresponding to a is greater than b. Okay, yeah, greater than b. Sorry, this one we are using. And for the last one, okay, for the last one, we will be using, okay, the less than b. uh, these values will be filled here. Okay, and we will look for common grouping, and accordingly we get the expressions for a is less than b. Now, do you all have any doubts as to how these expressions are obtained? Any doubts, please ask, so that I can explain. I'm assuming that you know all of these, so hence I am not getting into the equations. But if in case you guys have doubts, then yes, you can ask me, so that I can revisit as to how these expressions are obtained. Yes.
No, sir.
Okay, fine then. So we will now continue, and we will check, okay, as to how this can be implemented. Now, having the equations done, okay, once we have these equations, so now it becomes very easy for us, right? We have to just see as to what values are to be put. Okay, and you will have a1, b1. Okay, you have the complemented values of them, and then you have the true values and complemented. So which means it's it's a nice bet to have the true and complemented values, okay, connected along. So what we will do here is we will have a1 and a1 bar, a0 bar, b1 b1 bar, b0 b0 bar. So all the values will be here, the true and complemented values. So once we have them, okay, just look at one of the equations, and then accordingly you can connect them. And if an addition is needed, then yes, you'll be using an or gate. Okay, if not, then you'll be directly using your NAND gate implementation, right? So once we have these equations, it's very easy for us to implement them. And these values can be actually obtained, which is greater than b, less than b, and equal to b, right? Okay, so continuing our discussion, uh, students, any doubts here as to how we got this circuitry? Any doubts? Please be interactive.
No, sir.
Okay, fine. So the only key thing here is you will have to know what these equations are. Okay, and accordingly you can start implementing them. See, either you can implement using your basic gates, or even you can use De Morgan's theorem, convert them to standard format and use your NAND gates, right? See, NAND gates or your XOR gates are used here, your NOR gate is used here. Okay, fine. So now all these functions, okay, can be implemented with the help of your IC. Okay, so your IC, the number is 7485. Okay, so this will help us in actually implementing the function of your comparison. Okay, so what kind of comparison? Comparison which can help us in finding out if it's less than, equal to, or greater. Okay, so outputs will be here ultimately. So how is this performing this function? Okay, so for this, you should understand that it has its inputs. Okay, A1, A0, A1, A2, A3. Okay, so this is capable of how many bits now? How many bits is it capable of? How many bits of comparison is it doing?
4 bits, sir.
Exactly, 4 bits of comparison. So which means now you can imagine. Okay, and here this is given with our potential. Okay, so either it will be connected to high value, okay, or it will be connected to my low value, which is ground. Okay, so ultimately for my 1 I will be using VCC value, for my 0 I'll be using ground value. Now for the purpose of supplying no, of powering up the IC, I have VCC at 16th pin. Okay, so which is given a high value here. Okay, and the low value, the ground connection, is given to pin number 8. Okay, right. So here, how are we taking the values? We're taking the values by using VCC plus 5 and 0. Okay, so this will be taken as 1 and 0 accordingly, right? So I hope you have understood this concept here. Can I move on? Have you all understood the structure of IC now? Yes? Have you all understood the structure of IC? Can I proceed?
Yes, sir.
Fine. Thank you, Suprit, for responding. Now, we will move on and check as to how exactly this IC, works. Okay. So there is an algorithm here. Disha, thank you for you to responding. So there is a function table here. Okay. So all of you should understand as to what is happening inside the table. Okay, now as you can see, we had values from A0, A1, A2, A3, B0, B1, B2, B3. Okay, so just assume that these values are compared in parallel. Okay, so what we do is for A0, B0, I will have one column. For E1, B1, I will have another column, and for A2, B2, one column, A3, B3, one column. Okay, now I will check, okay, if the values are these are for comparison, okay, of inputs, and this is for cascaded inputs, and ultimately these are my outputs. So if you can see, okay, this is a normal one. Okay, this outputs that you have, okay, we have seen this previously also, which is equal to, less than, greater than, right? The same thing is being employed here. Just a moment. Okay, so here you have to understand as to how this table is occurring. Now, if you can see here, okay, we have 3 sections. One is for comparing inputs, the other is for cascading inputs, and the other is for outputs. Now, this So this section we have already seen, which is outputs, okay, the greater than b equal to and less than b. We have already seen this. Now, the important thing that we have to see here is when, let's take one case. Okay, let us take one case. In this case, okay, it will try to compare. Okay, suppose if it has only um, a3 b3, okay, then it will try to compare. If a3 is greater than b3, okay, just assume that it is like this. A3, then a2, then a1, and then a0. Okay, similarly for your b also, b3, b2, b1, and b0. Okay, so comparison will happen between these bits. Okay, a0 is compared with b0, a1 is compared with b1, a2 with b2, and a3 with b3. Okay, so this kind of comparison happens. So in this case, okay, what we are trying to see here is we are trying to compare bit by bit. Okay, and we are trying to check uh, if any one of the bit is higher, then it's going to be greater, or if it's not higher, then we can consider it as low. Okay, right. So here we are checking with a3 and b3 because we do not have anything here. Since a3 is greater than b3, so what is going to happen? Your a is greater than b, right? So we get this. Now in this case, okay, let's assume if a3 is less than b3. Okay, so what is going to happen for this? I will have a less than b. Let's say one more bit got added. Okay, so let's say I have two bits. Okay, so in that case, what is going to happen? It will compare if a3 is equal to b3. Okay, and the other case is if a2 is less than b2. Okay, now since all these are equal, okay, students, try to understand, since all these are equal, okay, it will this will not be considered. Okay, this will not be considered for my outputs because all are equal. Now here one more column is getting added, so in that case only this will be considered. Do you agree? Do you agree? Yes or no? Students, are you all understanding what I'm trying to say? Suprit?
Yes, sir. Yes, sir.
Okay,
Yes, sir.
fine, fine. So see here now, since a3 is equal to b3, I cannot decide what is my output because I have one more parameter here. What is that one more parameter? A2 is greater than b2. So since it's equal here, my output will be only dependent on this. Okay, so which means A2 is greater than B2. Okay, so this output is actually dependent only on the highest bit. Okay, only on the next bit, which is A2. Okay, right. So similarly, now for the less also, this comes up, okay, which is only dependent on A2, which is less than B2, right? Now let us take the next case. So in the next case, A3 is also equal to B3, A2 is also equal to B2. Okay, so I cannot decide my output based on these two values. Instead, I should consider here A1 and B1, right? Now, since my A1 and B1 are compared, okay, A1 is greater than B1, okay. So what is going to happen? Since A1 is greater than B1, I will absolutely get this value, okay, which is A greater than B. Any doubts here, students?
No, sir.
Okay, so ultimately this will keep going on, a comparison will keep happening, And when you come to this stage, for example, when you come to let's say, yeah, this stage, I cannot find out the value since all these are equal, right? So my deciding factor here becomes only A naught, which is greater than B naught. So my output here, final output, is actually dependent on A naught being greater than B naught, because all these are equal, right? So when it's equal, how can I say that A is equal to B? I cannot say that, right? So here A has a upper hand, okay, because A is higher. So ultimately my final output is going to be A greater than B. Similarly now, here in this case, okay, we can see that all are equal. Okay, since all are equal, so what is going to happen? Since all are equal, okay, uh, yeah, a3 is equal to b3, a2 is equal to b2, a1 is equal to b1, and a naught is equal to b naught. So in this case, okay, what is going to happen is a is greater than b is going to go high, okay, because we are cascading now. So we will start cascading. Till here we had not cascaded, right? So from here the cascading starts. So which means what we are trying to do here is we are trying to put them in parallel. So in this case, okay, in this case, when all are equal, then the IC will decide that your A is greater than B. So if it's greater than B, okay, whatever is the value here, the same thing will be your output. Okay. And in this case, when A3 is equal to B3, A2, then A naught, B naught. Okay. So when in this case, when all are equal, okay, and if A is less than B goes high, okay, if A is less than B goes high, then this output also will go high. In this case, okay, in this case, when all are equal, when all are equal, and if A is equal to B goes high, okay, then I'll be taking it as A is equal to B. Now, what is this actually happening here? Now we should go back to our uh, uh, circuit. Okay, we should go back to our IC and understand as to what is happening here. Okay, so for these three cases, when all are equal, okay, when all are equal, so when all are equal, so here whichever gets the high value, okay, this cascaded value is actually this. So here if A is less than B gets high value, then less than B will go high. If A is equal to B gets high value, then A is equal to B will be my output. If A is greater than B gets plus 5 VCC, then my output is going to turn on for A is greater than B, right? So students, any doubts in understanding this concept as to how the comparison is happening?
No, sir.
Okay, so ultimately what we are trying to do here is we are trying to compare one by one. We are taking all the cases bit by bit we are taking. See, it is just increasing here, okay, and at one point everything became equal, right? For all the three cases also equal. So it has all the kinds of permutation and combination here, and ultimately when all are equal, I cannot decide on the factor. So in that case, what I will do, wherever I give high, okay, that case is taken as high. Okay, so this is about your 1-bit and 2-bit comparators, and I have posted the screenshots also, wherein you can use that for your observation. Okay, so just make sure that you finish your observation and upload it, because it's all dependent on your performance. Okay, so any doubts here, students, with any concepts that we discussed so far? Yes, was it all clear?
Yes, sir.
Huh? Fine. Okay
Yes,
then.
sir.
Okay, so all you can do is you can start, you know, analyzing it. Okay, if any doubts, we can always have another meeting.